Around 1150, a mathematician named Bhaskara the Learned attempted to design a wheel containing mercury. He reasoned that as the wheel moved, the mercury would flow to the bottom of the reservoirs, so that one side of the wheel would constantly remain heavier than the other. He hoped that this motion would keep the wheel spinning forever. Bhaskara's design is one of the earliest designs for perpetual motion machines, which are devices that can spin indefinitely without an external energy source. Just imagine if there were windmills that could generate their own rotation, or light bulbs that could produce their own electricity. These inventions have been the goal of many inventors, because they could completely change our relationship with science. However, such machines have never met their intended purpose, because there is a small problem. They do not work. All ideas for perpetual motion machines violate the fundamental laws of thermodynamics, the branch of physics that explains the relationship between different forms of energy. The first law of thermodynamics states that energy cannot be created or destroyed. You cannot get more energy out than you put in. This situation prevents the dream of a useful perpetual motion machine from coming true, because a machine can only produce as much energy as it consumes. Nothing is left over to run a machine or charge a battery. What if you just wanted the machine to move on its own? Inventors thought of many things. Several of these were intended to be made like different variations of the wheels designed by Bhaskara. None of them worked. The parts that cause one side of the wheel to outweigh the other also shift the center of mass down below the axle. With a low center of mass, the wheel swings back and forth without continuing the motion, and eventually stops. Well, what if there were a different approach? In the 17th century, Robert Boyle thought he could make a self-watering pot. He thought that capillary action, the attraction between liquids and surfaces that pulls water through thin tubes, could allow the water to keep circulating around the pot. However, capillary action was not strong enough to overcome gravity and pull the water up. Differently, there are magnetic versions like a ramp set. The ball is supposed to be pulled upward by the magnet at the top, fall through the hole, and continue this movement without external support. This design also fails because, just like in the previous pot design, the magnet simply holds the ball at the top. Even if it were to keep moving, the strength of the magnet would weaken over time and eventually stop working. For these machines to keep their motion going, they need to create a little extra energy to help the system pass its stopping point, which means violating the first law of thermodynamics, as we mentioned. Today, there are machines that seem to keep running, but these do not produce infinite energy as imagined. Instead, they take the energy they need from the outside. Even if engineers were to design a machine that does not violate the first law of thermodynamics, this machine still wouldn't work, because of the second law. According to the second law of thermodynamics, energy tends to spread out through processes such as friction. Any machine, even if placed in a vacuum, will still have moving parts or interactions with air or liquid molecules that will generate friction and heat. This heat is escaping energy, and it will continue to leak, reducing the energy that powers the machine's own movement and causing it to stop. So far, these two laws of thermodynamics have hindered every idea related to infinite energy and the efforts to develop perpetual motion machines that inventors have dreamed of for years. Still, we do not know everything about the universe, so we cannot say for sure that we will never discover a perpetual motion machine. Perhaps we will find new, different forms of matter that will require us to revisit the laws of thermodynamics. Or maybe there is perpetual motion on very small quantum scales.